Classical Physics Tutoring, Chapter 1, Section 5, Rigid Body. Okay, so this is a big section to learn. It's all about rigid body. What is rigid bodies? Rigid body is, okay, we talk about point mass, and to describe the motion we use the center of gravity, and this is a point mass. The point mass will show you the trajectory and the motion. We can analyze all the basic motion of the material. This is Newton's mechanics, right? Now, rigid body is any 2 point in the body, the distance is fixed. So it doesn't stretch, it doesn't shrink. Next section is about the elastic body, and that deal with this type, the body stretch or shrink or twist or skew. But rigid body is the distance is fixed between any 2 point within the body. So it's rigid, like say steel or iron or rock, this kind of material. Okay, so in order to find out how it's moved, when it's moved, it may rotate like that, and also its moved position, right? When you throw a rock, it's moved. Okay, this parallel motion, we have a 3 degrees of freedom, X, Y, Z. That's what we dealt with using point mass. Now, rotational movement, this angular motion, okay, this rotate, and unless there is a fulcrum, the object rotate around center of gravity. Okay, center of gravity, and that's important. So say you give a force F at this point of the rigid body. So what happened to the rigid body? The rotational movement has also 3 degrees of freedom. Rotate X, around Y, and around Z. Okay, so total rigid body has 6 degrees of freedom. There's 3 different way to move, and in this we deal with 2D dimensions object. So actually we have 2 X and Y degree of freedom for the center of gravity, and also it's rotate. The rotation in this case is only 1 degree because it's rotate this way, X to Y, so it's rotate around the Z. Z is coming out from the screen. Okay, so when you have force applied to the 1 point of rigid body, the distance from center of gravity to this point become important. That's D. Okay, and force is divided into 2 components, the one parallel to D and orthogonal to D. Why? Because one parallel to D is going to cause, it's pushing the center of gravity. It's a parallel motion. Okay, motion, and the force component, which is orthogonal to D, this is D is a distance arm from center of gravity to the point of interest where the force is applied. Okay, and this orthogonal force is contribute to the rotational motion. Okay, now parallel motion, we explained all kind of parallel motion for the point mass, and the point mass basically cover everything about the parallel motion. Okay, so here we learn about rotational motion. Okay, parallel motion is F equals ma, right? And this component is applying to the center of gravity. So you take this component and apply to this, then you will know the motion of center of gravity. But rotational motion, how do we deal with it? Okay, so we manipulate a little bit the equation. dE over dt is mw d times f, and this m is, you take this small portion m, small mass, and we cover this on the circular motion equation, and the outer product of the d and f vector gives the sine component, which is orthogonal component. Okay, so this is the equation we had. You can go back to the previous video and review the circular motion section. And here the torque is md times f, right? Okay, so dE dt is actually omega torque. Okay, now the we are ignoring something here. See, this we have to put the vector which is coming out from the screen to be consistent on the equation. Okay, now torque is md times f, and that means d times m acceleration times d. So this is f actually, right? Because using Newton's equation, F equals ma, and the arm length, the radius times angular acceleration gives the acceleration, and this is the m is a small mass here. Okay, so if you manipulate this equation, then this is the multiplication of cross multiplication twice. So you go back to vector algebras, review that formula. We can expand this and end up with d square acceleration. So torque is md square acceleration. D is the length of the arm for the torque, and from center of gravity to the point of interest. Okay, and the point of interest we have small mass m. So total torque acting on rigid body is going to be integral of m is low at the point D, and dv, right? And we have a d square and acceleration, but angular acceleration is constant for any d, because the everywhere angular acceleration is same for the rigid body, and that means we can put I, angular acceleration. Torque is I times angular acceleration. What is I? I is integral of density, a distance from center of gravity, dv. Okay, so this is called moment of inertia. So we have an equation using moment of inertia, the same as Newton's equation. So this is for parallel motion. This is for rotational motion. Rotational motion, we take angular acceleration and torque. So dimension wise, you need to have a distance square within I, which is this. So this is moment of inertia. So moment of inertia is just like mass for parallel. The rotational motion uses moment of inertia. Okay. So what is the moment of inertia? We can calculate something like this: a disk spinning around, how much moment of inertia it has. Okay. We just apply this integral, and since it's a fixed width, then we care only about this circle area, which is 2 pi r and dr, and the distance is r square, right? And 0 to L, and you need to have a d. So that's the integral. So it's going to be something like that, right? This L, and 2 pi L square is the area S. You need to have a d, and ds together becomes a volume. So volume L square, this is already integral, right? So if the density is low, right? We need a low here. I forgot the low here. This is total weight, so it's end up with ml square. Okay, so the moment of inertia for this disk spinning in the middle is this equation. Okay. Next one, it's a ring. The ring is going to be easy because all the mass, the distance is constant. So we take L square rho dv, and this is m. So it's going to be L square m. Okay. Next one is a stick spinning on the one side. Okay, so we take x here. This is integration practice, right? I equals volume integral of rho x square, and dv is dx, and this with probably d, right? So multiply d, and that's gonna be 1/3 L cube rho d yeah the rho d, if this volume is dl, so rho d is going to be rho volume over L, and that's gonna be m. So 1/3 L square m, right? Okay. Okay, we keep repeating same way. The stick spinning around the center is going to be 1 over 12. Okay, the moment of inertia, you compare this and this is much lower. Why? It's more symmetric and easy to spin. This is much harder to spin. It's one-sided. Okay, so now we consider the circle is spinning at the edge, not in the middle. Okay, go through this integral, we will get this. Amazingly, the moment of inertia is very simple for this. Okay, so that's a moment of inertia. So the angular momentum of rigid body, when it's spin, how much momentum it has, and this is necessary for the case like when something spinning hit this kind of mechanics, the Newton mechanics, how much momentum is transferred. Okay, so it's going to be delta P n equals I a n. So this is impact caused by rotational movement. Do you remember that the delta P equals mb equals f dt? It's the same formula. Okay, and kinetic energy spinning body is I omega square 1 over 2. So that's the dE dt equals I with I omega, and if you take an integral, it's going to be okay. So what can you do with this the basic moment of inertia? Okay, suppose you have a spinning, it's a gyroscope, rigid body, and the one side is supported by this fulcrum, load side is L, okay, and the gravity is mg. What's happened to this? It's gonna just fall? Well, if you look at from top view, right, this is a fulcrum and it's sitting here, and when it's spinning around, it has the moment of inertia is spinning, so it has the I omega here, right? And any gravity force applied is going to be with L and mg, L times mg. So added vector is going to be like this. This is a top view. You look at from top of this, okay, which is this one. So the actually gravity give a momentum, I mean the torque, which is this whole things, this momentum is I2 angular acceleration. So it's become angular acceleration for this whole things. This momentum is I. Here, this one. Okay, so this I is spinning. You are adding this vector. So the new position is going to be here. So this whole thing is gonna move this way, make a rotational motion around this. Okay, so when you put something spinning with large moment of inertia, and this gravity doesn't make this fall. Instead, it's going to circle around this point. Okay, this is the gyroscope. And same thing happened to the top. It's called precession. What is precession? Precession is you have a spin, so you have a I omega vectors going this way. And if you add a gravity, this length L, it's give a torque. So it's going to add I omega to vector this way. So from top view, the top start spinning around here at the center. You see on the top, this is the center point here. Okay, so that's why the top, when it's tilted a little bit, it start moving around this, the fulcrum. It's called a precession movement. Okay, now the moon's face. Why moon is facing to Earth always the same side? Okay, recent discoveries. Moon has quite two different density. One side has the light, and another side is heavy. So heavy side, center of gravity, and light side, center of gravity, the distance is longer, L1, L2. So what's happened? The center of gravity defined the moon's orbit around the Earth, right? Center of gravity. But this uneven density is going to cause the different torque. Of course, this torque is larger T1 than T2. So the lighter material come this side, heavier material goes behind, and the moon shows lighter material side all the time, and that's confirmed by the recent the research by Chinese rover. This side has only light material like calcium and small atoms, and that's why Chinese was interested in going the other side to check the heavy material. It may have, like, mercury, gold, silver, those heavy material on the back. Okay, so this is the reason why the moon showed only one side to the Earth all the time. The lighter material and heavy material low density and high density. Its moon has an uneven center of gravity. Okay. So rigid bodies, the mechanics, Newton mechanics, give you the lever with fulcrum. That's fulcrum here, and as you know, L1 F1 equal to L2 F2. The torque is the same when it's stationary. Okay, so this is the generalized, and the fulcrum can be on the other side, and point of applying a force could be on the one side or on the both side. Either way, the basic equation is the same. Now, pulley. The pulley, you pull the load mg by this. Just think what's happened if you tie yourself and pull this guy. How much force do you need? Okay, so both sides, the tension is mg. If your weight is mg, then tension is going to be half of your weight. So if you do this, you can pull yourself up with half force. Okay, now same thing you can do by this. mg, the tension is half, so you need only half force. And if you don't want to pull up, you can pull down with half force. Important things about this half force is, in order to move the load by distance L, you have to move this side distance twice. So total work is the same. Half the work, half the force, but double the distance. So total amount of work is mgl. So this side mgl, you see, you don't save any energy. You just change the force and just use that force for longer distance. Now you can make it 1/4 because each time it's going to be mg half, mg half. This is mg half, mg half. This is quarter, half of the half mg. So that's what we got here. So what's happened to move this up by distance L? You have to pull this rope by 4L, right? Okay, so there's a pulley like that. There are two different diameter. So it's basically achieved the same thing. The torque for this and torque for this will be same. So diameter is different, the force is going to be different. And this is the game. When you hold the narrow side of the bat and fatty side of the bat, and you twist other way around, who win? Well, this guy has more torque, right? For the same force, because the radius is larger. Okay, so you can try next time with your friends. You hold the this side, and friends hold the narrow side, and you twist the opposite side. See who win. This side obviously win. Okay, the gear, its number of notches different, and this ratio define the gear's speed and the torque, the force. and the force ratio go by the gear's rate. And you can combine the gear, integrate the gear like that. You can make any kind of ratio. That's the mechanical design. Now slope, you have mg, and this force depends on the slope angle, right? But in order to move this L, you have to move longer L according to this slope. So total amount of work is the same, okay? So, but the force pulling up become much less than pulling up the load directly vertically. Okay, so it's the same thing, mechanics. And this same thing, the resistance from the wood go vertically here, right? So this is the force you give. This is called wedge. It's the same thing, same as the slope. You utilize the angle to give more force to drive in. Okay, let's work out some example here. Okay, this is example. You're holding this bar mg, the length is L. You suddenly remove your finger. So what's happened to this rigid body? Okay, let's consider the rotational movement. Okay, it's rotate around the center of gravity. So the gravity doesn't contribute to the rotational movement at all. It's hitting center of gravity. Okay, how much force was here right before you remove? It was half mg, right? So half mg, the force, times L/2, that's a torque, is going to cause rotational movement. And I, for this, going back here, is going to be this guy, 1/3. So I equal 1/3 L square m, right? So the acceleration, angular acceleration, is going to be so m is a weight. The mass, not the weight, m. So it's going to be 3/4 g. So that's acceleration. Okay. This angular acceleration is at this point. Let's see. Angular acceleration is at this point or this point. Doesn't matter. It's a rigid body. It's angular acceleration, same everywhere. Okay. So the angular acceleration of this stick is this. So if you consider the actual acceleration, now we got angular acceleration. How about the parallel motion acceleration? Parallel motion acceleration, we look at this center of gravity, and this point doesn't move. So this angular acceleration is going to cause the acceleration on this point, which is L/2. So we can say L/2 AN is going to be acceleration of the center of gravity, which is G. So the rotational motion is going to cause this much acceleration, right? But total acceleration is the G at the center of gravity. So parallel motion, motion's acceleration is going to be actually G minus 5/8 G. Okay, so the parallel, the moment you remove the finger, the center of gravity start making a move by this acceleration, and rotational angular rotation, the acceleration is going to be this value. Okay, so we describe rotational and parallel both. So it's kind of depend on the situation. You have to subtract the contribution from the rotation from the total parallel acceleration, and that's going to be the remaining acceleration for the parallel movement. Okay, so that means this point moved this way, and this vertical portion is going to be coming from this one, and this angular portion coming from this one. That's what it means, because this center of gravity doesn't go straight. Because of this, it's going to move this way, right? So it's going to be less than 1G. The 1G may go here, but it's because it's make a curve, the parallel acceleration will be less. Okay, so this is an example of how to apply our knowledge about the rigid body equations. I hope you enjoyed this video, and please move on to the next section, the videos, elastic body. If you like, please subscribe.